Okay, the last two on our list are going to be isodose line or normalization value, and then our inverse square law correction. We've talked about the collimator scatter factor, the phantom scatter factor, the fact that the combination of the two are the total scatter factor, a depth modifying factor, whether that's TMR or PDD, transmission factors of wedge factor or the tray factor. And we've talked about the off-axis ratio or off-axis factor and how that changes whether you have an open beam or a wedge beam. Next is going to be isodose line. Some people put norm here for normalization. Even though we're never going to give a straight 6x beam in the clinic, just for illustration, let's do this where we have a patient surface and we have a field, and let's just say we have our tumor target is here. And let's say we deliver, to keep the math simple, 100 monitor units, and the isodose lines look like this. Where we'll call this the 100% isodose line, and this is going to be the 95%, and this will be the 95%. Now you might ask, well, how do we get 95% on both sides? Well, if you remember the percent depth dose curve, this was 100%. Well, I have 95% here, and I have 95% here, because we have 95% in the build-up and then 95% in the build-down as well. So I have 95% on either arm. Well, you deliver 100 MU through the beam, and my 100% goes straight through the middle of the target. Well, we don't want that. We want the 100% isodose line to cover the target. So what can we do? Well, you can say, well, we can just calculate to a deeper point, right? True, we can. That in effect will be normalizing to a deeper, a different percent depth dose. Is the same thing as prescribing to a different isodose line. All this is it's normalizing. That's why these are all fractions, they're ratios. They're just normalizations based on where the point is at in space. So in this case, if we want to keep isocenter here, and we don't want to calculate to a different point, I can prescribe to a different isodose line. In this case, I can prescribe to the 95% isodose line. So I can say, okay, instead of the 100% being my prescription dose, I want to make the 95% my prescription dose. So I'm going to bump everything up 5% higher. So this is going to be 105. These are going to turn to 100. You might ask, well, how do we do that? Well, we just pump more MU in. So instead of 100 MU, I'm going to give 105 MU, roughly. So I'm just pumping more energy in to give me more dose. So instead of 100, I'm giving 105. Now my 95's turned to 100, 100 turns to 105, 95 turns to 100, and now my 100% prescription line looks like this. And I have treated the tumor to my dose that I want. The next thing is going to be the inverse square law. So let's see, we've done this, we've done that, we've done this, we've done this, we've done this, we've done that, we've done this. Last one is inverse square law. So inverse square law is going to be source to calibration point divided by source to calculation point squared. So if your machine is calibrated, let's take a simple example of 6X. If it's calibrated at 100 centimeter SSD for a 10 by 10 field size, 1.5 cm depth, okay, to deliver 1 centigray per MU. All right. Now, we don't treat SSD technique in the clinic anymore. For 99.999% of the patients, they're SAD technique, source to axis distance. Okay, we use a TMR or a TAR to calculate. And we do that because we want an isocentric technique. The gantries are mounted isocentrically, so they rotate 360 degrees around the patient. We don't want to have the gantry at a 0 angle and flip the patient upside down to do a PA field. We're way beyond that. So, but our calibration is calibrated at SSD. So how do we correct for that? Well, in this case, if I want to, we'll call this example 1. If I want to calc to isocenter, okay, my inverse square law correction is going to be source to calibration point, which is 100 centimeters plus 1.5 for the depth is 101.5. My source to calculation point is isocenter, which is located at 100 centimeters SAD. It's at the axis distance. This squared. So you get 1.03. So my inverse square law factor is 1.03. Well, what that means is I take the dose, if I have a number divided by a larger number, I get a smaller number. So my monitor units need to be adjusted lower to account for the inverse square law. Well, why do they need to be adjusted lower? Why do we need to adjust for it? Remember, let me draw the geometries. This is my source. This is the calibration geometry. I'm at 100 SSD, I'm at 1.5 centimeter. This is where I'm calculating 1 centigrade per monitor unit. Now look at my treatment geometry. Call this calc point. Look at my treatment geometry. In my treatment geometry, I'm closer by 1.5 centimeters. I'm closer to the source than 1.5 centimeters. This is where 1 centigrade equals 1 monitor unit. Okay, remember from the inverse square law lectures and examples that I've now moved 1.5 centimeters closer to the source. Okay, that's why we need to correct for it. So I get hotter, the radiation gets more intense the closer to the source I move. Therefore, we need to decrease the monitor units necessary to deliver the dose to that point by 3%, 1.03. Okay. What is the inverse square law for 15x, 18x, and 10x? I encourage you at your facilities to look this up and go ahead and calculate that. Another example would be that if our calc point isn't at the isocenter, but it's somewhere else, let's say it's 5 centimeters away from our 100 centimeter SAD. Okay. Now how do we calculate the inverse square law? Okay. Inverse square law is going to be the same thing as 1.015. That's our source to calibration distance. Source to calibration distance is going to depend on the facility that you're at as well as the energy that you're calculating. And now my source to calculation point is going to be 100 because I'm 100 centimeters SAD to the isocenter, and then I'm an additional 5 centimeters. So I'm 105 centimeters, and this whole thing is squared. Okay, this number is going to be less than 1. Notice that I'm beyond my 1.5 centimeter. This is where 1 centigrade equals 1 monitor unit. I'm past that. The radiation is getting less intense as I move past this point. Okay, I'm accounting for that by dividing my dose by a smaller number than 1. Therefore, I increase the number of monitor units that are needed. Make sense?